Okay, so what have we got? We've got phi, which maps G to H, homomorphism. We've got N is a normal subgroup of H. N is normal in N is a normal subgroup of G. And I've also got another relationship, which is N equals the kernel of phi. And we've established that G over N is isomorphic to the image of phi. And that's the first isomorphism theorem. That's great. You'll remember that G slash N, or G quotient of G by N, is the set of cosets Nx. So we had a nice little diagram like this. And these are the cosets in here. And that's the whole of G. Okay, so I'm going to give you a nice example of this. I'm going to give you an example. And the example I'm going to choose is, I'm going to represent it like this, and I'm actually going to say it's R squared under addition, and that's my group G. I needn't prove that that's a group because that's kind of obvious. But I'm going to have a subgroup of this, which I'm going to draw in blue, which is this line here, L. And because we know that this group is abelian, because A plus B equals B plus A, then we know that L is not just a subgroup of G, which is this group here. L is in fact a normal subgroup of G. So what I'm going to do is I'm going to find a homomorphism G which maps to another group H, phi maps G to H, such that the kernel of phi equals L. And then I'm going to talk about G upon L, the group structure on that, which we know is isomorphic to the image of phi by the first isomorphism theorem, but we're going to see it. So first of all, what I'm going to do is talk about what the cosets are, because you'll remember that this map, whose kernel is L, is the map phi, which maps R squared to L, such that phi of a point X, which I'm going to draw with an underscore, equals Lx. So it maps a point X, which is in R squared, to this coset here, which is Lx indexed by X. And you'll remember that if I choose two elements X and X dash that are both in the same coset, then they have the same image. And that's how we thought about the kernel of this image here. So I'm just going to go back to my picture. You'll remember that a coset looked like that. It was Lx. Now here I'm writing it multiplicatively. So you'll remember that I can write X composed with Y. I can write it in any sort of format I want. You might see a star, a little circle there, a little dot perhaps, or just a cross, YX instead of XY. Or you just write it like that. But these are all multiplicative notions. But because the group we've got is R squared under addition, I'm going to write it like that, and I'm also going to write it like this, L plus X. Okay? So these two things here, these are the same. Those two are the same. They're just written differently. Same thing, written differently. Through most of this course, we've been writing this is multiplicative notation, and this is additive notation. But they're the same thing because my group operation is just addition. Okay? So the first thing I'm going to do is work out what these cosets look like. So let's just draw my picture again. There's my plane. Here's my line here, L, which is there. The cosets are sets L plus X. So if I take a point here, which is X, there it is, X, then L plus X, well, I take this line here and just translate it up here, and I get another. I'm going to draw it in a slightly different colour. I'm going to draw it in red. This point here is X. There it is. That is the L plus X coset, and that point there is X. So of course I could have defined any point along here. Any point in the coset would do, yeah, and it would define the same coset. Let's take another point here. I'm going to write it in green. I've got a point here, let's say, and I'm going to call that Y. So again, we've got L plus Y, or Ly if I'm writing multiplicatively. I guess I could write Lx there in black. And that coset looks like that. And again, I could have chosen any point along here to be the representative. So, going back to black, the cosets of L in G, I guess, are lines parallel to L. Okay, I suppose I'd better prove that L is in fact a subgroup. Well, in fact, I'd better describe it first. L is the set of R times L vector, where L is a point on the line. Not the origin, I guess. Which I should say for completeness, origin. So you can see that if you get 2 points, we can see that 0, that it's R times L, where R is a member of R. Okay, so it's multiples of some particular point on the line. It doesn't really matter where it is, as long as it's not on the origin. So we might choose that point there. So L is things like 3L, 10L, minus 4L, and so on. And of course, 0L, which is the 0 vector, is the identity. And of course, if you have RL, then that to the minus 1 equals minus RL, because RL plus minus RL equals 0L. And it's associative as well. And you can see that it's a subset like this. It's relatively straightforward. Okay, so L is in fact a subset. So what we're looking for, we seek a homomorphism which what do we want? Which has L as a kernel. So what we're saying is that we're seeking a homomorphism phi such that phi of x is a homomorphism, and also, phi of alpha L equals 0, because these are that's my line L, equals 0. I guess it should be 0, 0 with an underscore on it. Let's just have a think about that. How are we going to order this? There's my planes. Here's my line, which does that. And so I'll get a point, and I want to make sure that my point here, any point on this line here, just goes to 0. So what I'm going to do that, I'm going to draw a line at right angles here. I'm just going to draw it as a dotted line here. This is a perpendicular. To L, and if I have a point X, I want to know what phi of X actually is. Well, I'm going to take it to that line there, where that's the right angle. So this point here is X, this point here is phi of X. So it maps it along there. So phi takes X to this point, and if you start here, it'll go that way to there, and if you start here, it'll go that way to this point here. But in particular, if you take a point on the line, it goes whoop, and takes it to the origin, because that's where this line meets the path. So how do we define that point? How do we define this mapping? So need to define this map. So if we just look at this, we know that x minus phi of x equals alpha L. Yeah? Because the distance from this point to this point is here, and that we've moved it parallel to L. And we also know that phi of x dot L equals 0, because L is a point, I'll use blue, L is this point here, and we're saying that any point on the line L is some r times L. So we know that phi of x dot L equals 0. So we can work out what phi of x actually is from this. That should be an underline there. Okay, so phi of x dot L equals 0. So from this one here, we can work out that phi of x equals x minus alpha L. And we know that phi of x dot L equals x dot L minus alpha L dot L. I'm still in blue, aren't I? And I shouldn't be. But we know that that equals 0 from here. So all I've done is taken this rule here, which says that to get from x to phi of x, I just move parallel to L. I don't know how far. I don't know what alpha is. I'll work that out in a minute. Yeah? So that's my first rule, that we've moved horizontally. We've moved parallel to L. And this rule here says that wherever we end up at phi of x, the dot product of that with L is 0, because this is a right angle here. So we know that 0 equals x dot L minus alpha L dot L, which tells me that alpha equals x dot L over L dot L. These are all being vectors. So going back to this equation here, which says that phi of x equals x minus alpha L, we know what alpha is now from here. So that says that phi of x equals x minus x dot L over L dot L, because this thing in brackets here is just alpha. So that's our homomorphism. That's it. Well, is it a homomorphism? We better check. So for a homomorphism, we've got phi of x, phi of y equals phi of x, y. That's written multiplicatively. But in this context, because we're using a cross symbol, what we mean is phi of x plus phi of y equals phi of x plus y. And of course it does, because this is linear in x. Well, let's just verify that. Let's work out which one should we start with. Should we start with the left or the right? Let's start with the left. So phi of x is x, and I'm just copying off here. Just a minute. Pinch it in a little bit perhaps. X minus x dot L over L dot L. Oops. L. And that's phi of x. Plus phi of y. I'll write it out here. Phi of y, which is x minus, oh no it isn't, it's y minus that, y dot L over L dot L, L. So of course I can factorise that. I can say it's equal to x plus y minus, well, what is it equal to? It's vector L over L dot L times x dot L plus y dot L, and of course I can use the normal rules of vectorisation to factorise that. X plus y minus L times x plus y L over L dot L, and that of course equals phi of x plus y, QED. So it's a homomorphism. It's a homomorphism whose kernel, well, we better work out what the kernel is. So 5x equals x minus L, x dot L over L dot L. And if I want the kernel, I've got to solve that equals 0. Okay? So I've got x equals L, x dot L over L dot L. What does that tell me? That tells me that x is parallel to L. Well, that's what we wanted. That's what we wanted. Why is x parallel to L? It's because that thing there, this thing here, is just a scalar. Because it's one dot product over another dot product, so it's just a scalar. So that's all right. So that's what I wanted to show. So what I'm doing is here. This is the definition of the kernel of phi, which is x that satisfies this relationship here, 5x equals 0, which is this, and I just mucked about with it and got this. So there we are. So that's my homomorphism. That's my homomorphism. So let's just have a look at the coset. Let's just have a look at the rules of G over N, which in our case is R squared over the line L. So what is the group structure? Group structure on the cosets. Well, written multiplicatively, we have, actually I'll go back to this one, nx composed with in the quotient group mapping with ny equals nxy. So that's written multiplicatively. So in this context we've got L plus x, I'll still use the circle, L plus y equals L x plus y. Okay, so let's have a look at what that means. L plus x, L plus y. So I'll go back to black. I'm not quite sure why I was in blue there. I've got to go back to blue now, of course. I don't like changing colours. Oh, blue, which is there. That's L. So if I have two lines, I've got this one here. There's an X, and I've got another one which I'll draw in green, which is there, and I'll put that one as a Y there. Again, you can see that I could have picked any X here and any Y there. Sorry, any X on that red line, and it would all come to the same thing, because remember we had to prove that the coset operation was well defined. So well defined meant it didn't matter what representative you chose, just any point along that line or any point in that coset will do. Okay? So of course what I'm going to do is draw, I'll go back to black. I'm going to draw my perpendicular in there, and so what we've got is that distance there, plus that distance there gives me a third coset right out here, which I'll draw in a different colour again. Have I got any different colours? Oh, I've got grey, I suppose. And this one here is L x plus y. So that's my coset addition. I think that's great, and I'm going to stop there. I'm going to give you loads more examples, but I think that's, in many ways, that's the best one. It's the best one because that's one way to visualise it, and it crops up in higher mathematics. It crops up in all sorts of tensor calculus and all this kind of stuff over and over again in a slightly different context. You normally see it in the context of vector spaces, but this will do. It's not ideal because the group is abelian, and so you don't see the great power of the assumption of the normal subgroup, because all subgroups of abelian groups are normal. So you don't quite see the edge that the first isomorphism theorem has got with this example, but it's pretty good. I like this example. I'm going to stop there.